Okay, we're back then. Hello. Okay, so now what's now? Verification, right? Formal verification.
Please.
It's important distinction. Okay, so what's formal verification?
Now all my students will be like, okay, do you know the answer? Tell us. Yeah. Well, I would say it's not testing, right?
Yeah, right. So okay.
You would want,
let's start from there.
from my perspective, we would say you would want a mathematical object that would guarantee that some code you wrote is doing what you would expect to do. So there are 2 points, right? In first, is the baby okay?
Mm-hmm. Yeah.
First, is the problem okay? How would you say what your program should do? Okay, so that's the specification part.
So the main idea, if I can maybe intervene for a second, is you have your program which exists,
yep.
Right? And then how do you verify it? Well, you use a different language. Maybe.
Well, I would contradict you.
Okay.
So you have your program, right, as you said, and then you need to say somehow what your program is supposed to do.
Okay. Yeah.
Right? Because that's just among of letters. Right?
The word verification means compare two things, right?
Yes,
usually.
Exactly.
Right. So you only have one thing, the program. So you need the second thing, right?
Yes,
which is
exactly.
Formal or
because I could verify my program, but against what? Against easy training outside, or against what, right? So you first need to be really sure what your program is supposed to do, and I think that's one problem, because it's not trivial to be able to say. I mean, even if you write the code and you say, okay, I want to I'm old and I'm not a programmer, right?
Okay.
So be gentle. So you say, I want to sort a vector. Okay. But even if when you write your program and that is sorting the vector, you still have some cases. Okay, what happens if if you have some unexpected behaviors in your program? What kind of numbers do you have in your vector? How do you?
What if the vector is empty?
How do you sort it? Ascending, descending, and so on. So you always have some cases, and
then even what does it mean for a vector to be sorted, right?
Exactly.
You have to describe it somehow, right?
What's the property? What's the relation between the elements, and so on. So you have to be able to say in a language what do you want to solve,
and in a formal language.
In a formal language. I mean, you could say in a natural language, but then you also want to be able to, first of all, others to understand what you wrote, because I can say in Romanian.
To precisely understand what you wrote.
Exactly. I could say this in Romanian, but then maybe I can say it also in English, but maybe my English is not so good, so I'm not using the precise enough words and so on, and you could understand something different than I actually meant when I wrote this, what my program is supposed to say, right? So that's not a trivial problem from my perspective, to be able to say what your program is supposed to do. And I know, okay, you write your code and you say, okay, but this is what I mean, but it's not
how
actually
do you
this,
check it,
right? Yeah.
Because you could definitely say that. Let's assume that, and this for me this feels a lot I would oftentimes feel this when I'm doing FP, right? Because when you're doing FP, you're describing things in a pretty formal way, right? It's not as formal as logic, or if you had to do it in.
No,
but it is quite formal, right?
From my perspective, you could specify something. If you have a language which respects some laws, then you are able to express something there, which is formal enough, because you respect that. You respect some laws, and you expect. You know what to expect, right? But of course, maybe your language is not expressive enough. So that's why you maybe need a better language, and so math is quite a pretty big language, quite expressive.
Yeah, but you usually don't
precise.
You're you don't use math period. You use some use some language that is maybe embedded in math, or uses some math, but you don't. So I think it's formal enough as well. And if the language doesn't have bottom like Agda, and such, you're pretty much giving formal definitions. Like you mean if you just write a program in Agda, then it's enough that the compiler compiles it, you mean? I'm not sure what you mean. Did I get it right?
No, but I think what I understand is like, okay, if you could specify also your properties in a language like Agda,
okay.
yeah, or.
Well, I mean, I think that's a bit of a. So when you do it, the way I see it in Agda is you write the type and you write the implementation, and in Agda allows you to have types precise enough that one verifies the other in a way, right? That your implementation verifies the type, and then you read the type and you think of, oh, okay, it's what I mean, right? Maybe, but then that's not. I'm not sure that's formally accepted as.
Yeah, there are several approaches to formal verification,
okay.
right? So there are different. As I said, approaches. So yeah, and then of course after you write your specification in a language, you have to get an object saying that, okay, my program is actually doing what it's supposed to do according to the
like, okay, you have the
specification.
program, you have the specification, you have to somehow compare them,
Yes.
right? And make sure they're the same thing.
Yes.
Somehow.
Exactly. Yeah.
And then it depends. If you're using a tool, you use the tool. If
Yeah.
you could have a manual algorithm to
Yes,
go
exactly.
from one
You
to
can
the
do
other,
it
right?
with paper and
it doesn't
pen,
have to. Yeah, it doesn't have to be a program. Although it oftentimes is, right? That's the way you do it.
Some kind of notation. Yeah. True.
Okay. So what are the okay, so we as FPers know about things like, for example, like we said earlier, okay, we can formally verify something by writing proofs in Agda or whatever, right? And then saying, okay, this is how things work.
Yeah, I think the hard part, I mean, not that I have experience with it, but I think the hard part is what you do with a program that you already have, and maybe in a language, not necessarily in a functional language.
I mean, even in functional language, it's not that easy to take a Haskell program and prove it.
Improve its correctness.
Right.
So, yeah.
So, okay, I think that the main takeaway here is that verification is really hard, right? That's one thing.
Yeah, and I think you have to think really well before you start to write some code, right? And I mean, in the sense, think really well in what you write your code.
I mean, obviously, the best code is no code, right? Like you don't have any code, you can't.
You don't have a problem, right? Yeah.
But like, in all seriousness, like, okay, are you aware of any tools that allow you to do large-scale verification, like regardless of programming language or tool or whatever? I might be asking the wrong question here, but like, I don't think there's a lot of that, right?
There's not a lot. I mean, you mentioned the company Runtime Verification we work from. We used to work for, and I think their approach is really healthy for doing formal verification. So basically, what they have a really nice logic behind their tool. So they have a tool called K-Framework, right? In which is based on matching logic, so it's not hand waving and so on. There is really
there's a ton of research behind
ton of research and really cool math behind. And what you have to do, actually, they done a lot of work on this. So, but the idea is you have to specify your language first in K, so such that after that you are able to verify your program in their language. But
so there's an additional step, right?
The additional step, you have to specify your language.
Your whole programming language.
The whole programming language. The good part is that they already did that for C and Java, right, so far. And I think
and
JavaScript,
and there's a few. Yeah.
And there's a few. So there are, I mean, you don't have to start from scratch. So, and after that, you can just give your C program and you could verify it. So I think, as far as I know, maybe that's one of the big tools you can use. It is definitely a big tool.
I think so. Okay, I really like RV's approach with K-Framework. It's very elegant, mathematically elegant, and then it works very well. But I think it works very well for small programs. I don't think it scales to like tens of thousands of lines of code. And I think this is a fundamental problem of verification, because I don't think I think it's very, very hard to formally specify. Like it's not any fault of K's here, of the frameworks. I think it's very, very hard to formally specify what a 20, 50,000 line program does, right? It can take you a lifetime, literally, to do that.
Yeah.
Right? While it could take you maybe a few months or maybe a year to write 50,000 lines of code, it will take you probably a lifetime to specify, like to formally specify everything that a system like that does, I think.
To specify what it's
Yeah,
supposed
yeah.
to do. Yeah, but if you start differently, if you before defining your language, you write the specifications. I mean, in my idea, it will be the best scenario would be you just write your specification and then you get your language by default. Or
You get you kind of specify it using and then the program is generated for you.
Somehow.
But then how you do verify it?
Well, I mean,
You have to trust the tool which generates the program, right?
not necessarily trust the tool, but the tool could give you like a certification, right? That it did what it's supposed to do. But let's look what...
So there are several theories approaches to formally verify programs. In FP, you often refer to calculus of inductive constructions, which is COC, or not only, right? Because you but anyway, I don't think you have to use COC. I think it's enough to have dependent types to do that. I'm not sure what COC gives you extra over dependent types.
But I think he's referring to the whole approach. So.
But if you have imperative code, sometimes you need to go for HOR logic, triples, and separation logic.
Yeah, I mean, also the K framework, as I said, it is a mix of it's a special case of COC was an example. Okay. It's a special case of not special case. It's a more general case than HOR logic, right, and separation logic, but. It's the same. You have to write some precondition, postcondition. So, and you give rules on how to do when you see a constructor from your language, or how you should react to the buildings you have in the blocks you have in your language, right? Yeah. So I think that's true for imperative code. Still have to HOR logic, separation logic is the way, which can be really improved, as the case with K framework, right? Yeah.
Okay, and then formal verification is expensive, but you don't always have to verify every component of your code, only the critical ones, I guess. Yeah, sure. That's a fair observation there.
I always ask the question: will you feel comfortable enough to have a surgery with the code you wrote?
No, never ever.
So that's scary that's a scary scenario for me.
Yeah.
I mean, not the code I write. I will never do this, but
I think that's true for if there's any one person who wrote the code that would do surgery for me, I would not be comfortable. Like if there's a whole process with multiple, like a lot of reviews and formal verification and so on, then maybe like that sounds better, right?
Same for
right.
Yeah.
Right. A plane. Right. I'm terrified of flying.
Yeah.
Anyway, so that's a very, very that example hits home.
Yeah.
Okay. So or cars. Yeah, like self-driving cars. Yeah.
Yeah, but for the car, at least you still feel you have some control, because
some
you can always.
You can grab the wheel.
But in a surgery, you're unconscious. For me, that's. In the plane, you're still conscious, but in a surgery,
I mean, even in the plane, even if you're conscious, what are you gonna do?
Yeah, but if I have my dad, like my dad used to be a pilot, so I'm airplane pilot, so.
Or the machine that cans food. Yeah, I mean.
Yeah, true. Again.
Yeah.
Scary. Let's be optimistic.
And I don't know how much. Like maybe for airplanes, a lot of it is like.
I think it is very.
There's a diligent process. Although there's been what was it, like the recent Boeing plane, which that turned out to be a hardware maybe awkwardness, which was attempted to be fixed by software, and it failed or something like that. If memory.
I think it was also something with the autopilot, and then they were.
So I think it was a kind of combination of something different with the hardware or something, or like with the methodology they used, and then they tried to fix it via software, and then it failed miserably.
Yeah, and then they somehow overlapping with the commands of the pilot.
Yeah, they wouldn't allow pilots, right, to take
Yeah.
control or something.
Yeah. Scary.
Yeah, that's terrifying.
Okay, so
So anyway, back to
formal verification
Formal
is
verification.
expensive, but
yeah.
I think, yeah.
So then, okay, so how do you feel about this new? I'm not sure how new it is, but it feels like it is gaining more and more traction. Right? It's kind of like Haskell. Right? Haskell has been there for 30 years or something, but it feels like it's gaining more traction recently,
Yep.
right? Or maybe that's true in our social bubble, right? It's always hard to know.
It's always a problem.
But anyway, like, and then this whole like quick check, quick spec, Quickstrom is a like recent library which is somewhat similar in concept, right? So like, how do you feel? 'Cause it's not formal verification, right? Because it's kind of it's trying out like it generates values and tries them out and sees if they respect some sort of laws, right? So like, do you have a sense of how useful that is, or?
Now I don't have enough experience with that, but I still, for example, of course, I trust more on FP code than some imperative code or some I don't know, other type of programming paradigm, because at least you have some math behind. For me, that gives me some comfort. If you have some,
they were wrong. I'm going to crash with this plane, but at least they use math to
yes, exactly so. Yeah, but I think you understand what I mean. I mean, even if you don't specify all the corners of your program as you did, or okay, at least you have some guarantee that, I don't know.
So Bolt said it is formal specification. I guess in a way, right? Because you use a formal language to specify the properties, but then the verifier doesn't give you a proof. It just tells you, okay, try the 100 of different inputs, and then none of them failed, right?
Yeah.
So like, okay, I agree with that. Like, you specify it formally, but you don't have a prover behind it, like, which can formally verify. It's just it uses that specification to try things out.
Yeah.
Yeah, I also think that it's like it's a huge like you give. Like, okay, there all can exist edge cases which you are missing when you're doing this, right?
Yeah.
But then it's a lot less expensive to do, right?
Yeah.
So
I think
it's a
the
good
balance,
middle ground.
the balance, it's middle ground. It's
I mean, obviously, it's a lot better than writing unit tests, right?
Yeah.
Which is like you just try to think on your own about the examples, because often, and especially, I think one thing that very, very few companies do, and something that I've been thinking about recently is, I think it's weird that the person who's writing the code is also writing the unit tests for the code, because you're oftentimes like biased by the algorithm you use, and you will write tests
you are in
that
your
test
chain
the
of
algorithm.
thoughts.
Yeah.
You
Rather
just,
than
you just how you say emphasize your thoughts,
biased,
right?
You're biased because you're thinking about a certain implementation rather than testing the algorithm, like the function or whatever it is, like the module. Which I think that's something that I might propose to my team. Let's try to like write tests for cross testing.
Yeah.
Instead, because like even when you review, like you're going to read the algorithm first, you're going to read the test last, and you're already biased by then.
Yeah.
And like even if you don't, it's not like it's your job to write the test, right? You're kind of like just looking at it and think, does it make sense? Yeah, sure, right?
Yeah.
But if you have to write the test yourself, then maybe you can think about other cases, other things. So there are some tools which verify programs or models to see if they respect the formal specification. Verification with LTL, CTL sometimes can be unfeasible due to the state explosion. If the model is very big, you can only get a very high degree of confidence. Yeah, and again, but that's better than like just programmer.
Of course, for a plane, you're not able to use this kind of approach, or maybe you could use it just for parts of it, right? But model checking and CTL, LTL is, if you have, for example, like the one you use when you have diabetes and you want to use like insulin pumps.
Yeah.
Yeah, that I know that these are some examples that are verified with
formally
with CTL, and you would want this, right? So yeah.
Okay, yeah, fair enough. But I think like also like for example Quickstrong, which is a tool that I've looked at for a bit and tried to do some PRs and like some improvements over it. Again, it's something like you end up with like weird areas of logic. For example, over there we ended up in some finite LTL logic, which like it's generally hard to find papers written about this, right?
But usually I think usually when you have a problem, you think of your problem and then you define your logic for your problem.
Okay.
That's why, of course, we know some logics, the mainstream ones, but there are thousands of logics, and especially because of verification. Because when you have a problem and you want to define the logic that suits better your problem, so maybe that's the case also here. You should define your logic. Don't forget about. I mean, of course, go and don't invent the wheel if it's possible, but maybe it's the case that you need a more custom logic.
I mean, sure, but it feels like a finite LTL it's kind of like a class of logic, not a specific. I'm just looking for, has anybody written what kind of properties exist for a finite logic?
I think most
like this, like linear logic.
Most of the logics they use they have infinite models behind, so infinite amount of time. So yeah.
Well, I guess this is something that we might have a look at together on stream at some point. That's not the announcement. We're not going to do that very, very soon, but at some point maybe we can try to do that, right? We can try to see if we can figure out a good logic for something like this.
Yeah, I would be happy to.
Yeah, that sounds like fun. I think like I have a vague idea because I read somewhere that a way to look at this is instead of looking in the future like LTL usually does, you can think, I'm at the end state and I'm looking back. Right?
Yeah,
there's obviously a finite amount of past time like steps, right?
Yeah.
And then that's easier to think about and to visualize, I guess, and then you can just kind of we can figure out what kind of properties this logic has, what kind of operators make sense, and like define laws between them or whatever. Right? That shouldn't be too complicated. So yeah, that's one thing we could be doing. Okay. So what else is there to say? Like, what haven't we said that you think it's important that we should say with regards to verification? I mean, of course, there's a huge and broad subject, right? So it's all okay. There's obviously a lot of things we haven't said about it.
Yeah, true. And I'm trying not to say the I don't know, obvious things. Yeah. Also, but you know more, I think, about than I know with dependent types, right? And then you also somehow catch the problem you have.
Yeah, right.
From the beginning, right, when you write your code. So
I wonder if
I think that's a really healthy approach. So
yes, but I wonder if it's considered because is it considered
formal verification
or not? Right, like because you don't really have like I think formal description and an implementation that you're verifying. Unless you think about type versus implementation, that's the only thing that could be reasonably considered. But is it? I'm not sure.
But at the end, it's a matter of but you have your certified somehow, right? You have your object that you receive at the end because you have an object behind.
Oh, yes and no, because in the end, like I think where this kind of dies down is if you actually try to write a program, inevitably your program will be some sort of I/O unit, right? So like at the root of your program, you cannot say anything about it, right? So I think running in I/O makes it so complicated. And actually dependent types can kind of alleviate that by having a very specific I/O type, which kind of precisely describes the operation that it's doing in a way. But right now, for example, even in Haskell, which we consider it's a safe language compared to currently popular languages like C or...
Okay, let's not give it
even that, like, consider like how the function which reads a file from this looks like. It's an I/O which gets a string for the path and gives you back a string.
Yeah.
It's like string to I/O string. it doesn't tell you anything about what kind of errors it can throw, and it can throw, right? What if the file doesn't exist? What if you don't have access to you don't have rights to read it? What if it's busy? What if you don't have enough memory to read the file? Like there's a ton of errors that could happen.
Yeah.
But the type doesn't describe any of those.
Yeah.
So like even in a language as safe as we assume Haskell is, doing things in I/O is very, very. The problem in Haskell is the prelude. I mean, yeah, of course, there's a ton of terrible functions in prelude, but even so, I don't think there is any library, like nobody in Haskell uses I/O checked exceptions with I/O. I don't think. So I don't know, like it's very hard because like you end up with an I/O unit if you do that. Like if you don't have an I/O which tracks all sorts of exceptions and precisely what it does, and even if it doesn't do that, right? Even if we don't consider exceptions, what's an I/O string? Does it come from a database, from a file, how do you verify that it does? Like what does it mean? Right? It's
yeah, but
like even so, okay, so with that you fix the error part. Okay, sure. You get terrible composition properties on that because then how you compose that with an either database reading error, right? It's very cumbersome. But then what about the string that you get back? What does it mean, right? You don't know what it means. It's just a string. Has it been read from a database, from a file, from network? Have we randomly generated a string? You don't know that, right? So how can you say what it does if you don't know that?
But I think if you, well, I don't think I know enough about this, but I think if you define, but at the end you still end up in the I/O. If you restrict your types more, right, somehow, and you don't, you could track down where your string is coming from. But I don't know if this is the right approach anyway for Haskell, right, of doing verification. So
I think what you're intuitively going towards is free monads, which is definitely a way to somehow not use I/O, but kind of create a DSL for what you would like to do in I/O, and then kind of combine those and verify those rather than the actual execution of things. And then maybe you assume that the interpreter is correct because it will be trivial, right? The read from file string will read from a file obviously, and then you can just implement it using the simple I/O function, right? And that's maybe a way to do it. To you can just verify the DSL instead of your program, but then not all programs are written with DSLs.
I think the big takeaway from this is that, okay, formal verification, I mean, there should be people, I mean, we should do much more research in formal verification, right? And maybe find some also new approaches or think a bit differently.
Yeah, but I think you got exactly that sort of solution in the end, right? Like DSL interpreting it is definitely one way to fix the I/O problem. Variants also help for error handling. Yeah, that's definitely true. But again, those are not available in Haskell, just in PureScript. But yeah, I think one thing that's very relevant whenever we're talking about formal verification.
What is PureScript run?
It's a library which combines variants with interpreters. It's a pretty cool PureScript library. I'll show you at some point. It's combining free model with variants. And I think I lost my train of thought. Oh yeah, no. So I think that the interesting thing about formal verification is that you kind of you can decide how much you want to put in, and that's about how much you can get out, right? Because you can, like you said, you can just pick a small part of your program, and that's maybe not very hard to verify, right? You can manually translate it to TLA plus or whatever, like at some existing tool which we know
use
has
some
been working
abstraction
for.
of your model.
And abstract your model, throw it in like some tool that already exists and does formal verification, verify it, and then you have like 5 programmers who just read that and make sure that it's doing the same thing. And of course, you can always be wrong. People can be wrong, but it's a way lower chance. And you verify the main idea or whatever. Or you can take parts of your program, verify components and so on with like various degrees of complexity or success, I guess,
Yeah.
right? But then I really like the fact that you can also do like property tests and even unit tests and even like all sorts of tests, right? Because like all of these are kind of, they have their place, right?
I think everything you do helps, right?
Yeah, exactly.
So from zero to, I mean, even a small amount of
Yeah. But I kind
giving
of
a
wish,
trust in your program helps. So
I kind of wish there was more publicity, if you will, around formal verification. But I think a lot of companies don't even consider it as
Yeah.
a real option, right?
but
Like
the
the
chat
de facto
already said
standard
this,
for-
it's expensive. So
Yeah, sure.
That's
Like the
why-
de facto standard for testing right now is just writing unit tests, right?
okay.
And nobody even thinks of like, I think even quick check things like this are not very well known outside the
Okay.
FP
Community.
world, right? So at least that would help in a lot of other languages, right? Unit tests are overrated. I mean, yeah, if you can write property tests, then yeah, definitely there's the sun like
Yeah.
hitting you right in the
We
face.
really need some
We need some
some shades.
shades, yeah. TDD is the overrated part. I'm not sure because like Didi was literally saying earlier, right? You were literally saying earlier that it would be better if you had the specification before
Yeah,
writing.
yeah, yeah.
And that's what TDD is, right? It's test-driven development. When you write the tests first and then you write the implementation.
Okay.
But then you usually write the unit test first, which is it's kind
Okay.
of okay. I don't want to say the words that I was
Should
thinking
just
about,
give more
but
importance to correctness.
yeah. So I think people in software engineering should have given more importance to correctness. It doesn't really need to be formally verified, but just having a certain degree of confidence by some sort of mathematical intuition would be a huge change. Yeah, I think a lot like
it would be a step forward.
yeah. In my experience, having worked for I don't want to count how many years.
Yeah, we're old.
Yeah, we're old. Is that like it's almost like if you bring up that you want to make a mathematical model of something, people look at you like as if you're insane.
Yeah. We should use a different.
We need a different name.
A code
We need to
name
rebrand
for math.
math. I
Yes.
know. We need to rebrand math. I know. That's the thing. We need an overhaul, right?
Yeah.
Like no more Greek. Like again, the beer doesn't really help much when I say that.
Yeah.
We need a hip new image, like a young hip person to be the forefront of math and be like, this is how you
Should
do
do. Probably.
it. Yeah.
Yeah. People are scared about math or.
Yeah.
I mean,
Yeah,
I think also among programmers, right?
Yeah, and programmers think, oh, why would I bother with that? I know what
I mean,
I'm doing.
I know how the students are, so what?
No, but like they grow up to be programmers, right? And
Yeah.
and then they're like, no, why would I do this silly thing where I think about all the properties and the laws in between the system or
Yeah.
whatever I'm doing? I've written this like 10,000 times.
Yeah,
I know
maybe
how to
it's
do this.
also our fault as teachers that we are not able to reach them more properly in convincing them how to. That's quite important to understand also these
maybe
ideas. So
maybe, but I guess like it's an
I always feel guilty for this. So
yeah, I don't know. Like it's weird to me that people don't get burned more often and then end up like because the way I got to FP was I got burned so much by bugs and
yeah, but
problems
maybe
and errors.
I
and
mean
then,
yeah, but it is quite too late somehow, right? I mean, you should convince them in their.
maybe it's one of the things that you need to fall before you actually believe your parents that it's going to hurt if you try something, right? So just teach students to be more rigorous and offer lightweight methods, tools to enable them to do so without very much mathy overhead. That would be an approach. Maybe, but I don't really like. I think we shouldn't be scared of math. And I get that you're trying to. I understand you're not scared of math, and you love math, and you would love to be able to do that. But I don't think. I think we should get people to love math rather than trick them that they're not really using math. If this different thing that's not math, don't worry about it, right?
And also this be more rigorous, right? I mean, we don't. As far as
But
I know,
when you're a student, right? So think about it today.
when you're a student, you're just happy it runs. So
You're a student, and then you get hired to do some JavaScript or Python or whatever sort of code, and you get a ton of money compared to most other industries.
Yeah.
You get paid a ton of money, and then you rarely face the consequences of your crappy software.
Yeah, you'll never get surgery with your tool, right?
Yeah, I mean, no, but like you're not gonna hire students for that, right?
Of course.
You're gonna hire students to do your like web application in API, which moves
Which is
data
not
from left to right and like does a food
Doesn't-
delivery, pizza delivery software, whatever, right?
In the worst case scenario, the pizza will get cold, right?
Yeah,
So-
you get the wrong kind of pizza, whatever. Who cares, right? Still pizza.
You
So,
really need the pizza.
I need a pizza. Yeah. But yeah, I mean, yeah, it's yeah, and then we just go. Sometimes, so all software has bugs. Don't worry about it, right? So yeah, it's job security. JavaScript will keep everyone employed forever. Yeah, exactly. Like it's not even job security, because if they thought that like doing this would help them, they might learn it, but they don't think it does, because very few people care about it. Very few companies care about it. So nothing is forcing them to do this. Maybe it is worth to let them burn too. Writing course operation is so boring. Yep, I know it is. So software engineering is very flexible, and I understand rigorous, correct code is not the standard. Yep, that's true. It's depressing not to have solid solutions for not wasting all day on that. Oh, crud. Okay. Yeah, I guess we. Maybe it's not trivial to do that. I'm not sure.